Chapter 3.3.1 starts with an example because what it's going to explain is how to solve problems that we're going to find in the future and that we've found so far. So what we're going to need is to set up a uh, way to solve our configurations. So let's start it. We know we have two grounded metal plates. Grounded plates means that there's no electric field here, positive, negative, and there's also no potential field. It means that the voltage can be equal to 0 as well as here, the voltage potential on these plates. And then there's a plate on the side which is kept at V0, and just a random value that is given to it. So we can solve this by using Laplace's equation. Now, as you can see, I only have two dimensions because we don't need z. As we get farther on c, it doesn't matter because all these plates just keep going and going, both up and down. So it's not dependent on c, but it's dependent on z, because as you get farther and farther from on the z-axis, you get farther and farther from the plate with the V0. Therefore, your voltage becomes 0. And when you get farther and farther on the y-axis, it means that you get farther and farther from the first plate. So it's going to matter in that too. So as you can see, it's only going to be a two-dimensional problem. So we're given the Laplace's equation that I already wrote down right here. And we're given boundary condition that we're going to prove right now. So the first boundary condition is that V0 when y is equals to 0. At y is equals to 0, we have these metals, this grounded metal plate. We already said that is the potential is equal to 0. So it is correct. Now the second boundary condition is that V is equals to 0 when y is equals to a. Now a is actually the value at which on the y-axis at which the second grounded plate is. So we know that at this point here there is this plate that we just talked about, the plate on top, and that its voltage potential is equals to 0, like you can see right here. So now the third boundary condition is that V is equals to V0 when x is equals to 0. As you can see, when x is equals to 0, we are on this point right here. So we are where this plate matters. And we said that the charge on that plate is V0. So it's normal. And the last condition is a little bit harder to see. But if you think about it, it's a little easy. If you get farther and farther from the initial plate, from the plate on the left, it means that the only thing that's going to matter is these two plates, which are 0. Therefore, the voltage is going to be approaching 0. Of course, it's never actually going to be exactly 0, but we can just say it approaches 0 as x approaches infinite. So as you get farther and farther, the voltage potential decreases, because we know that distance matters in our case. It's inversely proportional. Our voltage potential is inversely proportional to our distance. So as you can see, the problem sets the box sets up the problem as the voltage changes in the x and y direction, we said, out of the z, and that sets up two equations. I'm gonna write and explain. Sets up two equations. The capital X equation, which only depends on the x, and then the y, capital Y equation that only depends on the y equation. Now, in this case, it doesn't always work for us, but if we actually keep working on this, we're going to find every single solution to our problem. So now what we're going to do is divide our equation and rewrite it the way we should. So first of all, we're gonna take the Laplace's equation. So what we have up here, let me copy it and paste it. Okay. And we have to put it together. So we know that, for example, the partial derivative squared of v over dx squared plus the partial derivative squared of v over dy equals 0. Now let's imagine that we plug in the v for our things. So here we're gonna have x in the x direction and capital Y in the y direction, and then a capital X in the x, then capital Y in the y. Alright, so if you notice this capital Y with the y is actually constant when we derive it, because when we derive it by x, we have no x in our function. So we can just put capital Y in terms of y is equal to the derivative, times the derivative squared of our capital X in terms of x over d or times dx squared. Yes, sorry. Then same thing for our other function, but in this case we just take out the capital X within the x terms, and then derivative squared of our function y in terms of y squared. That also has to be equal to 0. Now, what we do is simply we divide both sides by v. And I said the v is equal to x times y. So the first part divided by x times y is going to be y divided by x in terms of x, y in terms of y. And then we're going to keep this one, it's only the same, plus then we're going to have capital X in terms of x divided by capital X in terms of x, y in terms of y. And then the second part is going to be the same. And then 0 divided by anything is simply going to be 0, so it's out say 0 again. So now we can simplify, and then we can cancel this capital Y, this capital Y, this capital X, and this capital X. So what we're left is 1 over capital X in terms of x, then d squared capital X over dx squared plus, I'm calling d the partial derivative, just easier to say, 1 over capital Y d squared capital Y over dy squared is equals to 0. So now, as you can see, we have two functions now. One only dependent on x, because you only have the x here and the x here. And then the other one only dependent on y, because you can see you have y here, and y here. So let's rewrite these functions as f of x plus g of y. Because we know there are two functions, and they're both dependent, one in x and the other one in y. So it works for us. Now we can solve these things. Well, in order to solve this, we have to say that these two together have to be equal to 0. Therefore, f of x has to be equal to negative g of y. But as you can see, they're in two different conditions, the two different terms. One is x and the other one is y. Therefore, these two things actually have to be two constant. So let's call the first constant C1 for f of x, and then the next one will be C2. And as you can see, if I were to bring C2 on the other side, I would have C1 minus C2, which is equal to 0. And therefore, C1 is equal to C2. Okay? Alright, now, what we do is we take what we were using before, so this part here, our f of x, we just said it's equals to. So we take our f of x, and we put it equals to a constant squared, which is going to be a k squared. And then for our y, we're going to put it in front of negative constant squared. So why one time positive, one time negative? Because as you can see here, C1 is going to be a positive value, and C2 is going to be a negative value. Because when they add it together, right here it will be plus, so here we negative. This is the opposite sign from each other. So we can switch it if we wanted to, and put negative here and positive here, but it's just easier to put it the way it is right now. So now let's start to solve this. Well, we multiply both sides by capital X of x, so we're going to have this part here, which will be erased, and this part here will stay the same. Let me actually go to the next page and recopy everything. Okay, so this part here we said it's going to be the same. Is equals to k squared capital X of x, and then we have this part here is equals to negative capital X under k squared times capital Y of y. Okay, so now if we try to solve it, this part here can be rewritten as capital X double prime equals to k squared. If you don't know this, this is how to solve second order differential equation. I'll suggest you watch that video on it. And then for this one, instead, we're going to have capital Y double squared, or just simply to make it y double squared is equals to negative k squared. So let's rewrite it. Here will be x and then y. So let's rewrite it to solve the second differential equation. So we're going to have r squared is equals to k squared, means that r is equals to plus or minus k. And then in this other case that we have that r squared is equals to negative k squared, which is a little bit more tricky, and I'm going to prove it to you. Alright, so we solve this, and we get that r is equals to square root of negative k squared. So why don't I put the plus or minus here in front? We'll see in a second. So we can simplify this and say that it's going to be equals to negative square root of 1 times k squared, square root of negative, negative square root of 1 times square root of k squared is going to be equals to I times square root of k squared, which is going to be ik. Now, if I take this and I square it, I'm going to have square root of negative 1 times square root of k, and I'm going to square both. So I'm going to get negative 1 times k squared, which is equals to negative k squared. And if I plug it in our solutions, I get that r squared, which is what we did, because this is simply r, works. But if I instead put a negative in front, then everything will have a negative in front, and as you can see, I'll end up with a positive, and that doesn't actually solve our thing, because positive k squared is not equal to negative k squared. Okay? Okay. Let me erase this. There we go. So the first solutions is going to be e at the power of, x power of x. Terms of x is going to be e to the power of k t plus e to the power of negative k t. With of course constant in front that I'm going to call a and b. The second one instead, we only have one solution. So it's going to be y, capital Y, sorry. In terms of y, is equals to e to the power of, as you said, our solution was positive ik, so ikt, which can be written as a cosine and cosine function. So we're going to rewrite it as, actually here I would have to call it, let's call a constant in front z. Probably get confused with this. Let's call a capital constant something t, capital T, because we won't use that anymore. And so we can rewrite this, because we have an imaginary number at the exponent, as c sine of k y. Oops, sorry. Here I forgot to write. Instead of t would be the y, because it's in terms of y, and here instead of t would be in terms of x. Sorry, x, because it's in terms of x. I'm just used to the k problems. Plus d cosine of ky. Okay. So, oops. Alright, so we have these two solutions now to our problem. There are two different equations, but what if we put them together? We said that v of x and y is equals to capital X in terms of x times capital Y in terms of y. So it's going to be our capital X, which is simply going to be this part over here, times our capital Y, which is this part over here. There we go. And so this is our general solution. Now, though, one thing that we did at the beginning was knowing some initial conditions. Because if we go back and we look at our boundary condition, these parts over here, we can actually solve some of it. Well, let's try and copy it first of all, and then paste it over here. Okay. Now, the first thing we know is that v is equal to 0 when y is equal to 0. So v is equal to 0, so 0 equals to our function, which is a e power of kx plus b e power of negative kx when y is equal to 0. So we're going to have c sine of k0 plus, so k times 0, times plus d times cosine of k times 0. As you can see, the sign over here actually gets cancelled out when we solve this, because the sign of 0 is 0. And then this part here actually equals to 1, because sign of equals to, well, in this case, 1 and then times d, so d. So in our case, we don't get 0 unless we say that d is equal to 0. So we already found one of our solutions. D is equal to 0. So let's rewrite what we have, our function, with d is equal to 0. So we can simply erase the last part, and this is our halfway solution. We have other initial conditions that we can prove. So now, let's look at our second condition. V is equal to 0 when y is equal to a. So v is equal to 0, so again, equals to 0. And then a, x is the same value always. So I'm going to copy and paste it in. And then c, sine of ky. As you can see, we can solve this and see that if we plug in 0 for y, if we plug in a for y, and sine has to be equals to 0, so we're going to have that sine of ka is equals to 0. Therefore, k has to be equals to a certain value, which is going to be n pi over a. Because then, when we plug it in the function, we're going to get sine of n pi times a, n pi over a times a, which the two a cancel each other out. So we're going to have sine of n pi. And of course, as long as n is an integer number, so it's going to be equals to 1, 2, 3, 4. Sine is going to be equal to 0. Also, 0 in front, So as long as it's equal to that. Now, why can it actually, it's fine like this. Alright, so we know that k is equals to this value over here now. And we can go and plug in our solution. So let's just take this one that we have over here, go down, and paste it. This one is our voltage. Do it in black. X and Y we said. And instead of writing k, we're going to write the solution that we found before. That is, k is equals to n pi over a. So, is equals to a e to the power of n pi over a plus b e to the power of negative n pi over a x, and x on this side too, forgot. This times c times sine of n pi over a, so n pi. Okay, so our third function tells us that v is equals to v naught when x equals to 0. So let's go in and let's plug in x equals to 0. So v of 0 and y, so we don't know what y is equals to 0, so it's equals to what we have here. So we're going to have a, then e to the power of 0, which is going to be equal to 1, so a, plus b, all times c is equals, all times c times sine of n pi is equals to v naught, v naught, not 0, I don't know why it was there, v naught. And there is another thing that we can think of, we can use, but not exactly right now. The other thing that we can use is number 4. So we know that v approaches 0 when x approaches infinite. So how do we use this? Well, let's try it. V of infinite, comma y, is equals to 0, is equals to a times e to the power of infinite, which we can put in the calculator. If we try to actually graph our function e to the power of infinite, we're going to get a function that is approaching 0 when it's a function that approaches 0. So we will get that e is equals to 0 when the x is equals to infinite. So we're going to get 0 plus. Then if we plug in infinite for our x, we're going to get a negative infinite. Oh, actually, sorry, I miscounted the other one. So we will get a infinite for negative b. We'll get a 0, so we get b times e to the power of negative infinite, which is equal to 0. Then a e times n pi over a times infinite, which is simply infinite, would be actually equals to infinite plus this value times c and n pi n pi. Sorry, yes. So the only way we can solve this would actually be a times infinite times c, so n sine of n pi, or would actually be put a is equals to 0, because if a is equal to 0, then we're gonna have that we're gonna have 0 times infinite, which is simply 0, plus 0 times c sine of n pi, doesn't matter in our case, which is simply going to be equals to 0. So this is one other solution. So we know that a is equals to 0. We also know that k is equals to n pi over a, and we also know that d is equal to 0. So let's go back and copy our initial solution, the one that we have right here, copy it and paste it over here, and let's write it as the final solution. So we know that a is equals to 0, so this one gets written off, d is equals to 0, and we also know that k is equals to n pi over a, so let's rewrite this. So b e the power of negative n pi over a x times c times sine of n pi n pi over a y. So this will be our final solution. Now it's run a little differently in the problem that we have on the book, because as we found before, actually here, we know that b is equals to 1, and we will have to find c. Also, it doesn't write k as n pi over a, so another way of writing it would be e to the power of negative kx times c sine of ky. That would be another solution to it. Then, of course, you have to use Fourier series to solve was c in our case, but that's another video.